the next learning unit in the chapter PV system components. In this lesson, we will deal with batteries. In the first unit of this chapter, we learned that in some PV systems, batteries are integrated. While a short time ago lead-acid batteries were predominantly used as storage in solar systems, lithium-based storage solutions have become more and more popular in recent years. To better understand the integration of a battery storage into a PV system, let's first take a look at the structure and basic operation of a lithium-ion battery. Each lithium-ion battery cell consists of two electrodes, a negative electrode and a positive electrode. The electrodes are each composed of a current collector and an active material applied to it. Between the electrodes there is an ion-conducting electrolyte which enables the necessary charge exchange. To ensure electrical separation of the electrodes, a separator is installed in the electrolyte that is permeable to lithium ions but not to electrons. The negative electrode of the lithium-ion cell consists of a copper foil and a layer of carbon. Graphite is often used here because it has a low electrode potential and exhibits low volume expansion during charging and discharging. The positive electrode consists of an aluminum collector. A variety of different material combinations are used as active material on the positive electrode. Essentially, iron phosphide or metal oxide, for example cobalt, manganese or nickel oxide, are used here. In the charged states, many lithium ions are embedded in the graphite layers. During discharge, lithium ions migrate from the anode through the electrolyte and separator to the cathode, where they are intercalated. The oxidation process that takes place simultaneously releases electrons which flow to the positive cathode via an external electrical connection. There, a reduction process takes place, electrons are absorbed and the lithium ions are deposited in the cathode material. The external current flow allows electrical loads to be operated. During charging, exactly the opposite process takes place. Lithium ions migrate from the cathode to the anode, where they are stored reversibly. As long as no charge or discharge takes place and no current flows, a certain voltage is established between the two electrodes. This voltage depends on the material combination of the active materials on the electrodes. In today's systems, voltages of 2.2 volt to a maximum of 4.2 volt per cell are achieved. In most cases, this voltage is too low for practical use, so several battery cells are usually connected in series to form a module. Such a module is also called a battery pack. When several cells are connected in series, the voltage can be increased. However, series connection also means that if one cell fails, the entire battery pack fails. With a parallel connection, on the other hand, the voltage remains the same, but the maximum discharge current increases. By combining parallel and series connection, the electrical parameters of the battery can be specifically adjusted. In addition to the interconnected cells, the battery system consists of various other mechanical and electronic components. The mechanical components mainly include the housing with insulation and, if necessary, cooling and mounting system. In addition, a battery management system is required, which monitors, among other things, the electrical parameters as well as the temperature of the storage unit and switches off the battery in the event of faults. To understand what exactly the battery management system is needed for, let's take a look at the most important parameters of the battery. A battery is basically a constant voltage source with a certain nominal voltage. Typical values for the nominal voltage are 12 volt, 24 volt or 48 volt. However, the actual voltage of the battery depends on its current state of charge. A fully charged battery usually has a slightly higher voltage than the nominal voltage. As it discharges, the voltage then slowly decreases and eventually becomes lower than the nominal voltage. For further consideration, we will assume a voltage of 12 volt as an example. A certain amount of electrical charge is stored in the battery, which can be delivered to the consumer at a nominal voltage. This is the capacity of the battery. The electric charge is usually measured in units of coulombs, but the capacity of a battery is often expressed in units of ampere hours. Since the unit of amperes equals to coulombs per second, one could of course convert this specification to coulombs. In practice, however, it is helpful to specify the capacity in ampere hours, since from this it can be calculated directly how long the battery can supply a certain current. An example: a battery with 50 ampere hours can supply a current of 1 amp for 50 hours at nominal voltage, or 10 amps for 5 hours. Now, in practice, the amount of energy that a battery can deliver is often more of interest than the amount of charge. The energy capacity is simply the product of the capacity and the nominal voltage. The battery from our last example with 50 ampere hours and a voltage of 12 volt thus has an energy capacity of 600 watt hours. If the battery is now discharged, the remaining amount of energy naturally decreases. The state of charge, or SOC, indicates the remaining amount of energy in relation to the energy capacity of the battery. Instead of the state of charge, the depth of discharge, or DOD, is often used. It corresponds to the ratio of the amount of energy already extracted to the maximum energy capacity of the battery. A short example: a battery with an initial capacity of 600 watt hours is discharged by 60 watt hours. So 10% of the energy is removed. The state of charge of the battery is still 90% in this case. The depth of discharge is 10%. Another important parameter is the efficiency of a battery. There are various ways of defining the efficiency of a battery. In practice, the so-called energy efficiency has the greatest significance. It corresponds to the ratio between the energy that can be extracted to the energy supplied. Typical values for the energy efficiency are about 80% for lead batteries and 90 to 95% for lithium-ion batteries. Let me give you an example. Let's imagine a battery with an efficiency of 95%. We now charge this battery and put, for example, 100 watt hours into it. When discharging, however, we can only withdraw 95 watt hours from it. In the course of its life, a battery is frequently charged and discharged. In the process, its capacity gradually decreases. The cycle life of a battery is defined as the number of charge-discharge cycles after which the battery has only a certain charge capacity left. In general, 80% of the nominal capacity is used for this purpose. A charge cycle describes the discharge or residual capacity of 0% and a subsequent charge to 100%. In the fictional case of the lithium iron phosphide accumulator shown here, the remaining capacity has dropped to 80% of the initial capacity after 3,000 to 4,000 full cycles. The service life is therefore at least 3,000 cycles. Although manufacturers often give a fixed number for the cycle life, in practice it depends on a number of factors. For example, the depth of discharge and state of charge have a large influence on the cycle life. If the battery shown here is only operated in full cycles, so it is always discharged to 0% and the recharge to 100%, this results in the shown cycle life of 3,000 to 4,000 cycles. If the DOD, the depth of discharge, is now limited to 80%, that means the battery is never discharged below a state of charge of 20%, the cycle life increases to 5,000 to 8,000 cycles. However, these are only partial cycles, so the entire available capacity is no longer used. If the DOD is limited even further, the cycle life can be further increased. In addition to the depth of discharge, the temperature also has a significant influence on the cycle life. This is due to the fact that the reactivity of the electrode materials increases with rising temperature. This speeds the aging of the accumulator. In addition to high outside temperatures, high temperatures are mainly caused by high currents, meaning a heavy load on the battery. Finally, let's take a look at the economic efficiency of a battery storage system. Here you can see again the development of the feed-in tariff and the electricity purchase price in Germany for the years 2000 to 2022. In 2022, the feed-in tariff in Germany for a small PV system is 6.7 cents per kilowatt hour. The electricity purchase price, on the other hand, is 34.6 cents per kilowatt hour. That is a difference of 27.9 cents per kilowatt hour. Hence, the battery storage will only be economic if a stored kilowatt hour is cheaper than 27.9 cents per kilowatt hour. So let's try to roughly calculate the cost of one stored kilowatt hour. Let's, for example, have a look at a lithium iron phosphide battery, which is sold specifically for use in PV systems. The chosen model has a capacity of 11 kilowatt hours. The retail price in 2022 is 6,380 euro. The efficiency of the battery is 96%. The manufacturer specifies the service life as 10 years at one full cycle per day. We thus assume a discharge depth of 100% and a cycle life of 3,650 cycles. We disregard the decrease in capacity over the lifetime here. For an exact consideration, this would of course have to be taken into account. To calculate the price per stored kilowatt hour, we divide the sales price of the battery by the amount of energy that can be stored over its lifetime. This is the product of the capacity with the efficiency, the depth of discharge, and the cycle life. For the battery shown here, we get a value of 17 euro cents per kilowatt hour. We must not forget, however, that this is only the pure storage cost. The power generation costs are not yet considered here. Nevertheless, we can already see that the cost per stored kilowatt hour is well below 27.9 cents per kilowatt hour that currently separates the electricity purchase price from the feed-in tariff. Let's look at the values of a lead-acid battery for comparison. The investment costs for the lead-acid battery are significantly lower. However, lead batteries usually have a much lower efficiency. We generously assume 85% here. At a discharge depth of 50%, the manufacturer specifies a cycle life of 900 cycles. With these values, we get a value of 47 cents per stored kilowatt hour for the lead battery. This is almost 3 times as much as for the selected lithium-ion battery. This comparison explains why lithium-ion batteries are increasingly being used in PV systems instead of lead-acid batteries, which were the norm until a few years ago. It is only through the continuous further development of lithium-ion technology that the use of battery storage for increasing self-consumption is becoming economical. Let us summarize. Important characteristic values of a battery are its energy capacity, its state of charge SOC, and its depth of discharge DOD. We have seen that the capacity of a battery storage decreases over its lifetime and remains at 80% after reaching the so-called cycle life. Cycle life depends on various operating factors such as DOD and temperature. Despite the higher investment cost, lithium-ion storage is more economical than storage with lead-acid batteries, mainly because of the higher cycle life. Thank you for your attention.